Hi everyone, Senan on this side, and in this video we are going to see how do we solve this LeetCode daily problem, which is make sum divisible by p. Before we get started, I have a whole PDF solution provided in the description below. You can just check out that GitHub link and you can easily download this document with the code, time and space complexity, approach and intuition, so that you don't have to watch the video again and again and again. So let's get started. So what is this question asking? So question is saying make sum divisible by p. So given an array of positive integers nums, remove the smallest subarray, which could be empty, possibly, such that the sum of the remaining elements is divisible by p. It is not allowed to remove the whole array. Return the length of the smallest subarray that you need to remove, or -1 if it's impossible. A subarray is defined as a contiguous block of elements in the array. Fine. Now let's look at this code and this test case basically and figure out what is happening here. So first of all, what is the sum? Sum is what? 3 plus 1, 4 plus 4, 8 plus 2, 10. And 10 cannot be divided by 6. So 10 modulo 6 is 4, right? So if you look at this test case, when you sum them, you get a value of 6. When you divide that by p, you get a value of 2 or the remainder as 0. Since this sum is divisible by p, we don't have to remove any subarray. So that is why we return 0. So this is this case, possibly empty. But since in this case the divisibility is not achieved, that means a remainder of 4 is there when you divide this by the sum of this nums by p. So if you look at this, what I could do is, in the brute force way, I could figure out all the subarrays, right, whose sum moduloed by p is this remainder, which is 4 in this case, right? 10 modulo 6 is 4. So I could see this is 4, the sum is 4, and I remove this subarray. The remaining subarray, which is 4 and 2, is actually divisible by 6. Or else what I could do is just take this 4, remove this subarray of length 1, and see the remaining sum is what? It's again 6, which is divisible by p. So since I was able to find two subarrays with sum modulo p as 4, I can find the minimum length of that subarray and return that as my answer. And that is what we are exactly going to do. This is the idea. A couple of things. Since if you look at the constraints, the length is 10 to the power 5 at max. So I know it could be a solution of n or n log n, just looking at the constraints. And at n square, there is a possibility to get a time limit exceeded. Okay, so because of that reason itself, I assume that it's a solution of n and n log n. But as we discussed, you could generate all subarrays to check if there's sum modulo p is actually the remainder, and you need to find the minimum length of that subarray. So you need to generate all the subarrays. So that means we have to use something about n square, because that is what it takes to generate all subarrays. So yep, doing n square, you can actually solve this problem. It might give you a time limit exceeded. I did not check that, but it could or it could not as well. That's one thing. Another thing is the answer could be n or n log n. That's what I'm assuming, right? Assumptions can be wrong, could be wrong, just giving you an idea. Now since I'm seeing that the location of elements where they are placed is important, right? I cannot just rearrange, because we are trying to find a subarray, not a subsequence but a subarray. Because of this, the location of the elements are important, and that is why we cannot use any algorithm which uses sorting as a solution, because sorting would change the location of elements and we won't be able to figure out if it is a subarray or not. So that's one thing. So we remove the idea that the possible time complexity could not have a log in. Other thing is, I cannot find a binary search idea in this as well. There's no min and max ranges for a possible solution. Also, technically there is from 0 to n, but how do I do the searching, right? Now when I say that, I can actually, or could I? Okay, so I'm not exactly seeing a binary search solution exactly. Could there be? I don't know exactly. I'm not thinking a lot. So I'm assuming this is more or less big of n solution, and the reason for that is we are finding sum of a subarray. And when you find a sum of a subarray, you clearly know what I'm talking about. It's the famous prefix sum, and that is what we are actually going to use. So the approach would be to first of all compute the remainder of the total sum by p, and that is what we are going to do. You get the n, you get a variable total, and you do total is equal to total plus num modulo p. Now, why are we doing this modulo p? Because you see, the maximum value is 10 to the power 9, and we can have 10 to the power 5 occurrences of that 10 to the power 9 elements. Or, yep, 10 to the power 9. 10 to the power 5 occurrences of 10 to the power 9. That is somewhere about 10 to the power 14, right? The sum could be 10 to the power 14, and we know the fact that integer cannot store that big of a value. So what I do is I take the modulo operation at each and every step because we require that itself. We don't require anything else. Now I do is at the end, after the final iteration, total plus num modulo p. If this value total is 0, that means the sum is divisible by 0, so we return 0. Now if that is not the case, we go and check around this. One more thing before we discuss this part, I just want you to know I initialize the min length to n because that is the maximum possible thing that you can actually remove. And what you could do is uh, after, let's say, after doing this for loop, we have this algorithm is correct, assume that, and if min length is still n, we were not able to update this min length, that means we don't have a possible solution, so that is why I return -1, so to take care of this statement. Now otherwise, if I was able to update this min length which is less than n, because we are doing a minimum operation, right, I return that min length. So I know the value is between 1 and n, exclusive of n, inclusive of 1, because we've eliminated 0 here itself. Now what we are going to do is use a prefix sum idea to figure out how to use this hash map to find the answer. So what I do is for each element in the array, I would compute the necessary remainder, which is the search that I use, and try to adjust with the current prefix sum, right? So that if I remove this subarray, I would actually get the actual possible length of a subarray that has a value 4 in this case, or 3 and 1 of length 2. So how do I do that? The idea is simple. The idea is using that what is the smallest length of the subarray starting from any index, let's say 0, right? So at every iteration, what I'm trying to ask is, starting from index I, what is the smallest subarray? If I remove that, I would actually get a valid solution, and I would ask this question for each and every index itself. That is what I'm trying to do. So you update the min length if and only if you found that search previously. So prefix plus nums of I would modulo p. So this is the prefix sum, right? Now the way that I'm calculating this thing is similar to what we did in yesterday's LeetCode problem, the logic of the modulo operation. So what you do is prefix minus total. So this is, you want this total, right? So this prefix sum, I take this prefix, right, and I find another prefix that I found earlier, such that when prefix minus total is also divisible by, so it gets me the 0 divisibility for the total prefix sum. So what I do is, given this prefix, I find a number, subtract this by total, and I find a number, a different prefix that I might have found previously. So when I take that previous index, the location, the prefix of the previous, how do we say that? The location of the previous prefix that I found till the current index I. If I remove this small subsection or subarray, right, I can have a value of the total array divisible by p, removing this subarray. That is the idea. So I get this search, and I do modulo dot count, or basically I'm trying to search in this dictionary, right? So count would return either 0 or 1 because it's a dictionary, and dictionary cannot have unique different same keys for multiple elements. So this would either return 0 or 1. It's better than doing the find because the syntax is very complicated. So I do count, and since I found a search, so that given at this index I have found a previous prefix, such that if I remove the subarray starting from the previous prefix that I found till now, I would actually get the total sum divisible by p. That is what I'm trying to search, and then I update this. Okay, so that is the idea. And after every iteration, I update the current prefix with I, right? Because we need to find the minimum, the smallest prefix, the smallest length of the subarray, not the largest. Otherwise, if you wanted to find a largest, you could, I think, you could actually do the else part in this as well. To add else, you would technically, I think, get the largest thing that you have to remove, but that won't make sense because if you remove the whole subarray, that's a possible solution. And in the end, I have initialized this min length as n because you can remove everything, right? So if min length is equal to n, even after doing this operation, that means there is no possible solution. And since there is no possible solution, I return -1. Otherwise, if I was able to update this min length to a value lesser than n and greater than 0, that means I have a solution and I return that minimum length. One more thing, I declared a value of prefix and search outside, and I used this in this dictionary or the map. I said modulo 0 is -1 to keep track of 0 as well, to keep track of 0 prefix as well, the sum 0. So yep, that is the whole idea. Other thing that you could do is you could just take this down, and rather than having 0, you could just use the prefix. But I'll go with this itself. That's more clear. What is the time and space complexity? Space is what? Modulo and modulo prefix, right? So what are the possible prefix values? So I'm always doing a modulo p. So you can have a value from 0 to p-1. So basically p elements, and p has a value of range this, and nums of I also has a value of this. So let's say this size of nums is n and this is of size p. So this is running for okay, so I was talking about this modulo, right? Space taken by this modulo. The space taken by this modulo is big O of p in the worst case, right? Or big O of n, let's say. I don't remember. Okay, I'll see my document first. I'll verify that. What have I written there? So yep, updating this, doing this operation is a constant time operation, and the space complexity for this is big O of p, the modulo, this dictionary, and what the time complexity for this is big O of n, and for this as well it's big O of n. So the total time complexity is big O of n, and the space is big O of p, right? Big O of p. But when you think it closely, how many prefixes you would actually have? You observe that we are going into this for loop for big O of n times, and at max you could have big O of n prefixes in your modulo list. So by that, this space complexity of this map is not big O of p but big O of n, because you can at max add values to this big O of n times. So this is bounded, the size of this bounded by this n again. And since n is smaller than p, I can clearly say that the space complexity is also big O of n and not big O of p. So for this solution, both time and space is big O of n, and that is what is the solution for this. One more thing I would like to discuss is in my document itself. Okay, so yep, at this position I made a mistake that it's not return 1 but it's return -1. I've already uploaded this to the GitHub page, so just keep this in mind. Yep, so again, space complexity big O of n, not p. This is big O of n. Yep. So that is the video. Thanks for watching, and I'll see you in the next one.